Welcome back, everyone. We've done lots of theory. Now we need to do some calculations, okay? So make sure you got your calculator with you, and let's get going. Right. So here's our question. A lead ball of mass 0. Oopsie, didn't want to do that. There we go. Of mass 0.5 kilograms is attached to a long light string. Why do they tell us that it's a light string? Because they're telling us we can ignore the mass. It's not going to make any difference to our calculations, all right? They tell you it's allowed to swing from a height of 1.5 meters above its equilibrium position. Here you got to remember for me that when we work out potential energy, we have to know where the height is being measured from. So because they're saying from the equilibrium position, that's when it's at the bottom of its motion, it really doesn't matter whether this pendulum is 3 meters above the ground, 2 meters above the ground. That doesn't matter because that distance sort of falls away when we do the calculations. What I'm concerned about is its difference in height when it moves, okay? And the equilibrium position is when it's at the bottom. So this is the position where we say potential energy equals 0. My first question is to calculate the maximum velocity of the lead ball. What we need to say to ourselves is, first of all, number one, it's a pendulum, so it's a circle. That tells me I can't use equations of motion. We're good with that. Then they ask for maximum velocity. So we've got to look at our diagram and go, where would the maximum velocity be? Well, it's going to be here. No, it's not. That's minimum. It's going to be here. Sometimes you've got to rethink these things, okay? When it gets, remember, it's going to come down. When it gets here, at the bottom, it has 0 potential energy, maximum kinetic. Then it goes up, and over here, this point, it actually has to stop before it can come back down. So at this point, its kinetic energy is 0. I know that over here, velocity is 0. Over here, height is 0. We need to be very, very, very careful. We know, because energy is conserved, that all the potential energy it has when it's at the top of its motion has become kinetic energy when it gets to the bottom. But I can't just go potential at the top equals kinetic at the bottom. We have to show that we're using the conservation of mechanical energy. That means I need to go the mechanical energy at the top of the motion, so I'm using a T for the top, is equal to the mechanical energy at the bottom. That means I'm going to take the potential plus the kinetic at the top. That's going to be equal to the potential plus the kinetic energy at the bottom. We need to now do some substitution. First of all, I don't know the potential at the top, so I'm going to have to work it out. So that's mgh, and that's the top height. Now, I know kinetic energy is equal to a half mv squared, but I also know the velocity is 0, which means that the kinetic energy at the top is 0. That's going to be equal to the potential at the bottom is 0 plus a half mv squared. We've done most of the science now. Let's put in what values we know. The mass is 0.5. Gravity is a constant at 9,8. And they told me the height was 1.5. I'm not going to put the plus naught anymore because plus naught, the naught disappears. So now we have a half times 0.5 times v squared. All we have to do now is the maths. If you can use your calculators really well, you know how to all do this in your calculator, and you want to do this all in one step, please go ahead and do that. But don't forget, it's v squared. When you get to the end, you must square root it. So what I'm going to do is I'm going to make my life a little bit easier, all right? I want to show you the maths. So v squared is going to be equal to a half times 9,8 times 1,5 divided by, and a half is 0.5 times by 0.5. Okay? I'm going to put that into my calculator because I definitely can't do that in my head. So here's the top part. So 0.5 times 9.8 times 1.5. I'm going to divide that by 0.5 times 0.5. I'm not worrying about the fact that I've got a fraction right now because that's v squared. So I now need to take my answer and square root it. So I'm going to take my answer, I'm going to square root it, and we never leave it like that, and we get 5,422. Oopsie. Of course, I can just go into the next page. 5,4, what was it? 22, so it's going to be 5,42 meters per second. We don't worry about direction on here, okay? What happens though? Now we're going to change this up a little bit. I'm going to say to you, I want to know the velocity of my ball when it's 1 meter above the ground. Now we've got to think carefully. I can either compare to when it's at the bottom or when it's at the top. So I'm going to call this was the top, this was the bottom, and I'm going to call this position A. I'm going to use conservation of mechanical energy. I don't want to use the velocity I found at the bottom, because what if it was wrong? But I can use the same thing as I just did. So we're going to go the mechanical energy at the top is equal to the mechanical energy at point A. So this was potential plus kinetic energy at the top, which is the potential plus the kinetic energy at point A. At the top, this was mgh. This was 0. Now I don't have another 0. Now I've got mgh at point A plus a half mv squared at point A. So 0.5 times 9,8 times 1.5 is going to be equal to 0.5 times 9,8 times 1 plus a half times 0.5. Okay, this is fun maths. So let's do this, all the little bits and pieces for this one. So we've got 0.5 times 9.8 times 1.5, whoopsie, 1.5, not 11.5. And that gives me 7,35. All right. Let's do the other side. So we've got 0.5 times 9.8 times 1 gives me 4,9. And this is a half times a half, which is 0,25. Let's just double check that, just in case my brain has gone to sleep. 0.5 times 0.5. There we go. Let's get VA squared on its own. So we're going to go 7,35 minus 4,9, all divided by 0,25. So let's quickly do this. Ooh, okay, so we've got 7.35 minus 4.9. Don't forget to say equal. We're going to take that. Whoops, you divide it only once. 0.25. Now, I need to take that answer and square root it. And we get 3,13. Much smaller than the velocity we had when it was at B. Why? Because there's still potential. But the same thing has happened. The potential has changed into kinetic, but the total kinetic energy stays the same. Sorry, total mechanical energy stays the same. That is the constant, all right? And it doesn't matter where in the motion we look at it, your potential energy plus your kinetic energy always gives you the same total, okay? So, we've spent some energy. It's time to recharge. So we're going to take a short break, and I'll see you in a couple of minutes.